Welcome to homework.
So in this question, we have a common isotope of uranium experiencing a decay into this element of 234Th. I'm actually not sure how to pronounce this, but it's a different element, and it decays by an alpha emission because we can see that its mass number decreases by 4. So in part A, we're given its half-life and we want to find the decay constant. So the relationship of half-life and decay constant is decay constant is going to divided by the half-life. So all we need to do is put in all the numbers. The half-life is in years, but we need to convert it to seconds. Times years times years per second. I think it's also in the index about how many years in a second. So 3.1476 times 10 to the 7th second is a year. Okay, and this gives us around 4.92 times 10 to the negative 18 second inverse. Okay, so that is decay constant lambda. What mass of uranium is required for an activity of 1 curie? So we have delta n of delta T of the rate equals lambda over n. We want the amount of n so that the rate equals 1 curie. So we put n to the left hand side, and equals delta n over delta T over lambda. And this is equal to, so firstly, we need to convert curie to Bach. My curie is 3.7 times 10 to the 10th Bach. And lambda is, we already found, 10 to the negative 18 second. This is 7.52 times 10 to the 27 nuclei. Great, so that's a number, but it asks us for the mass. So in order to find the mass, we also need to use we need to multiply the number of the nuclei by the mass of each nuclear. The mass of each nuclear we can just quickly estimate by the mass of all of its nucleus. So the mass of its nucleus, each nucleus is 1.67 times 10 to the negative 27, and then I multiply it by 138. Of course, this is not exactly accurate because we know there will be a binding energy, there will be a mass impact. But for the precision we're looking for here, it's enough. So it's 3 times 10 to the third kilogram, so 3 tons of mass. And the last one, how many alpha particles are emitted per second by 10 grams of uranium? So let's find 10 grams of uranium. We need to first find how many uranium there is in 10 grams. So it's again 238 times 1.67 times 10 to the negative 27 kilogram. This gives us there are 2.52 times 10 to the 22 nuclei. And then we can find the rate. The rate is lambda times n equals 4.92 times 10 to the negative 18 times 2.52 times 10 to the 22. So it is 1.24 times 10 to the 5 decays per second. So this is the alpha particles that will be emitted. So this is the rays the alpha particle will be emitted for with 10 grams of uranium.